We now move on in our electricity discussion to using electricity to deliver medicine. And that's what our iontophoresis is. It's not chapter 6, it's actually chapter 13. So I'll put up a different comic so you can see that. So it's chapter 13. This part, wait, where's my little, there it is. The 285 is definitely correct. So that's good to know. So yeah, exactly what I just mentioned. We are going to use the electrical current to push medicine. So if we put some medicine on an area that we want to deliver medicine to, then throw some current on there, and that's where we're using these electrically charged, what we call ions, and it's pushing it in there. Does it work? Man, if it does, right, if it does work, we can deliver medicine directly to an area that we really want. It looks like some shin splints going on here. We can deliver it right where we want. We don't have to go through, taking a pill, going through the stomach, getting absorbed that length of time, and then it's going throughout the entire bloodstream. Nope, we deliver it right now, right where we want it, and don't have to wait. So it's a good, in theory, man, that sounds like great. Now, does it work? Actually, it does. There's some pretty good evidence out there that says this actually works, in fact, a lot better than phonophoresis. But the foundation that, and really the depth of penetration is a good one. This is a superficial, so we're not getting super deep with our medicine, but we can if it's superficial, like the shin or pretty superficial structures. There's a good likelihood that we can get that medicine in there. All right, foundation wise, we got to know Coulomb's law. This is my law, people. Not really, but it's my name. Coulomb's law, I mean, I know everybody knows this. This is such a common thing in our society, right? Radial, inverse square, proportional. We've heard it so many times. No. Really, here's what I want you to know. The Cliff Notes version of Coulomb's law. Like charges repel, opposites attract, or unlike. So I guess I can put opposites in there. In fact, I think I'll do that on the next slide. Yes, that's what I want you to know. Like charges repel, opposites attract. That is the foundation. If you can remember that as I ask you questions about iontophoresis, you're going to be able to figure these things out just by knowing Coulomb's law. This is the key. I've given you this diagram in your notes. It's on our Brightspace page. This to me is a good way to gather everything you need to know about iontophoresis is in this little diagram. And so this kind of gives us our basically, I'm going to explain this really quick and then I'll go through it. But really quick, so we have our two electrodes. We have a negative electrode. The negative electrode is usually where most of the negative ions collect. That's where the negatives are coming out. Same thing with the positive electron. And so really, if you look at, all right, how am I going to push? If I want to push certain medicines, that's exactly what you guys see here. Negative electrode, negatively charged drug or solution, it's going to push that away into the skin. That's what you see here. These little triangles are getting pushed into the skin. These little square positives getting pushed into the tissue. Yay! Thanks for that. Now, the other thing that happens, because that's the opposites, that's the like charges repelling, but the opposites attract part in the tissue, right? So in the tissue, we have these free ions, charged particles, that start to be drawn to the opposite side. So that's where I've drawn these little positive charges, little negative charges. Look at there, that's good. And so you can see, though, that phenomena, you need to be able to explain that. If I say we have a negatively charged solution or drug, where are you going to put it? Well, I want to push it away, so I'm going to put it under the negative electrode. Same thing with positive, right? The effect of that inside the tissue, then we're going to have positive, always positive ions get drawn to the negative electrode, and negative ions get drawn to the positive electrode. Got to know that. So if I ask you that, remember Coulomb's law. Now, I drew these electrodes, one's bigger than the other. I don't know why. Yeah, I do. Because where there's positive collection of ions, all these little positive ions are going to collect under this area of the skin. You get this alkaline reaction. Negative, you get the acidic reaction. Yes, you have to know that. And then the alkaline reaction is more likely to cause a electrical burn. And so that you'll get, it's not so much of a burn like you burnt your steak or your hamburger, but it does cause damage to the skin, and we don't want to do that, right? So that's why I have a bigger negative electrode, because I'm dispersing all of the, right, because we know about density. A bigger electrode has less density, so I'm kind of spreading out all these positive ions so we don't have such a concentrated alkaline reaction. If you look at and count all these right here that are kind of spread out, it's the same number of positives as there are negatives, but the negatives are all kind of, bunched up together. That's okay, because the acidic reaction doesn't cause the burns as bad as an alkaline reaction. So bigger electrode, spread those babies out. All right, that's pretty much it, right? So if you can look at this diagram and explain what, or understand what I just explained, or then explain it to somebody else, you're going to be in good shape to answer questions about iontophoresis. The rest of the PowerPoint just goes through and tells you what I just told you, right? So, starting off, negative electrode has negative ions, positively, right? So we got that, right? We all know that the like charges are going to repel. So negative ions are pushed away by the negative electrode and vice versa. That's where our acidic reaction occurs, and then you can see the alkaline reaction occurring at the positive. Alkaline reaction is right here, where we got these positive ions moving away from the positive electrode. Wait, I think I said that wrong. No, this is kind of wrong. So no, this is right. So the positive ions right here are moving away from the positive electrode, and then toward that negative electrode, and that's where the alkaline is that right? So that's right. It's written correct. I confused myself. So look, positive pushing away these positive, that's good, but it's also going to push away all these free electrons, these free ions, and that's where it's going to cause that alkaline reaction. Basically, you need to know alkaline reaction under negative electrode because there's positives, acidic reaction under positive electrode because there's a bunch of negatives. Boom. That's what we got to know. There's the chemical burn, more likely under the alkaline or the negative electrode. So that's why we use that larger electrode to decrease the density. All right, a couple other concerns as we go through here. I'll go through here pretty quick because it should be pretty straightforward. We know that water-dense tissues are going to conduct electricity good. So skin and fat are not water dense. To get the electricity to go through that, we got to turn it up, and that could cause some problems. So we got to be careful on those areas, and we need to make sure we have good conductance and that kind of stuff. You can see some of this. Sweat glands are good. Skin impedance right here, the skin part, does decrease with time, so that could cause some more issues as well as we go through there. This is also a super important one. The waveform. Typically, it's direct current. Your book under that area, it says iontophoresis, parentheses, direct current, right? So we want, if we're going to push, and I'll talk about this a little bit in class, if we're going to push a certain charged fluid, we don't want to change our poles, right? We want one electrode being the same charge the whole time. Push, push, push. Just keep pushing, baby. Keep pushing. Intensity doesn't really matter, especially it does matter, but I'm not going to make you guys remember it and that kind of stuff. There is some protocols that talk about dose-oriented protocols. So you get something like this, where you go, all right, we're going to do 40 milliamps per minute per dose, that kind of stuff. You do not have to note this unless you actually do it, and then when it comes to that point, then you can kind of follow directions, and that's all you're doing. Ultimately, typically what we do is the low amp currents work a little bit better. Low amp for longer periods of time work better, but really the intensity is just turned up till the patient feels it, right? And so we're not trying to get any contractions or anything special out of it. Just let them feel it. Let them feel it. You can see duration, how many times that we do, that kind of stuff. The electrodes are pretty kind of cool. They're unique. These have they do have a little chamber where you'll put the medicine in there. This is actually a complete unit here. So this would be the one pole and another pole. So this might be positive. This might be negative. That kind of stuff. These might be just normal pads that you attach wires to, and they just have a little chamber for the medicine. So you can see all the rest of that. That's just some basic stuff that you can and we're still going to set it up the same way as we do a stem. We'll talk a little bit more about this in class if you have some questions, but definitely read the 5-6 pages in your text to kind of get an idea of what your text is saying. It's a lot of the same stuff. And then there's a table and the different medications. You don't have to memorize the medications, but just to give you an idea of what kinds of medications are used. And it's mostly anti-inflammatories and pain meds, right? So there's that. So that's the extent of this one, and we can talk about stuff in class. I have some fun pictures taking you back to the Lightning McQueen days. This is kind of an old movie now. And then one more fun picture that I think is kind of cool, the way they set that up.